So here we have a computer chip that's encased in some sort of insulating material, and it has a volumetric heat generation rate of Q dot, units of watts per cubic meter, for example. We know that the sides and the base of the chip are insulated, and the goal here is to calculate an equation for the temperature profile and graph that. A couple of things that we know: so there's air flowing over the top of the chip, and we know a heat transfer coefficient H, and we know the temperature of the room T infinity. So heat's being generated within the chip, and it's being convected out into the surrounding air. A couple of assumptions we're going to make is that the temperature is independent of the x-coordinates. So the temperature at these two locations are the same, and the temperature at these two locations across the z-axis are the same. So what that means is that temperature is only a function of y. So let's zoom in on the cross-section of the chip, with the y-axis starting at the base of the chip, and the thickness of the chip is distance L. The first thing we want to do is simplify the heat diffusion equation. We know it's at steady state, so the term on the right is 0. We know that the temperature is not a function of z and not a function of x. So what we're left with are these two terms in the heat diffusion equation. Moreover, let's assume that the thermal conductivity is uniform throughout the chip, and we'll pull K out of that term. So this then is the simplified heat diffusion equation. We could integrate this once. We'll find that dt dy is equal to negative q dot over k plus some constant of integration. We'll call that C1. And if we integrated this again, we would get a second constant of integration. And so because we're dealing with a second order differential equation for temperature, we need two boundary conditions. So I'll write these as BC1 and boundary condition 2. And remember, when we specify a boundary condition, what we're actually doing is specifying a function that is valid at a particular value of y. So we need to think about what's going on at, in this case, at y equals 0 and at y equals L, the top of the chip. Well, because of the insulation, boundary condition 1, let's just evaluate at y equals 0, and what we know is that the flux is equal to 0 at y equals 0 because the base of this is insulated. We can also write the flux as being negative k dt dy, and that's equal to 0 at y equals 0. So when you think about whatever equation we're coming up with for the temperature profile, one of the things that we know is the boundary condition at y equals 0. Whatever the temperature profile looks like, we know that the slope has to equal 0 at y equals 0. So that gives us one boundary condition. Some other things we can think of intuitively is because the heat is being generated and flowing upward out of the chip, we know that the slope dt dy has to be a negative quantity everywhere from y equals 0 to y equals L. We can apply the first boundary condition. We'll find that C1 is equal to 0, and it's equal to 0 because dt dy is equal to 0 at y equals 0. So in doing so, we'll simplify this equation by removing the first constant of integration. So if we integrate this a second time, we'll find that dt dy is equal to negative q dot over 2k multiplied by y squared plus a second constant of integration. So looking at this, we know right away that the temperature profile has to be quadratic in nature, and it must be concave downward because of the negative sign in front of it. So our first boundary condition is that dt dy is equal to 0. So this, for example, could be our temperature distribution. It's a parabola. One thing that this first boundary condition doesn't tell us, though, is how high or how hot the temperature is at the base of the chip, because both of these are satisfying the first boundary condition. So we need some more information here at the surface of the chip to try to pin down where that parabola is located. So to get at that second boundary condition, we're going to have to do an energy balance around the entire chip. The energy balance, we've got the rate at which energy is being stored is equal to the rate at which energy enters minus the rate at which it leaves, plus the total rate at which energy is being generated. At steady state, the rate at which energy is being stored goes to 0. For our control volume for the whole chip, there's no way for energy to get in. So what this means is that the energy leaving the chip is equal to the rate at which energy is being generated by the chip. Note that both of these have units of watts, and the rate at which energy is being generated is equal to the volumetric heat generation rate Q dot multiplied by the total volume of the chip. The total volume of the chip is equal to L multiplied by the area on top of the chip. The energy leaving the chip is also equal to the thermal flux minus the area at the top of the chip. So now we have a way to relate the thermal flux to the rate at which energy is being generated. And note that the area of the chip itself doesn't play a role with this relationship. So we'll find that the flux Q double prime is equal to Q dot multiplied by the length. Double checking the units on that Q dot, we have dimensions of watts per cubic meter. The length, we have dimensions of meters. So we're left with watts per meter squared, which is the flux at Y equals L. And on the outer surface of the chip, we have one other relationship. We know a value for the heat transfer coefficient, and we know a value for room temperature. So a second expression for Q double prime, which is valid at Y equals L, is equal to H times the surface temperature of the chip minus T infinity. And on the graph, when we define the surface temperature, it's valid at Y equals L. But one of the problems is that we don't know what the surface temperature of the chip is. We have to position this vertically, so we're going to have to solve for Ts somehow. To do that, let's equate the two equations for flux. So now that allows us to solve for the temperature at the surface of the chip. So Ts is equal to Q dot times L divided by the heat transfer coefficient H plus T infinity. Double checking our units on that better have units of temperature. And so Q dot is watts per cubic meter, length is meters, and 1 over the heat transfer coefficient is meters squared Kelvin per watt. And simplifying this, we find that watts cancel out and cubic meters cancel out, and we are left with units of Kelvin, which is good. So, because we know the volumetric heat generation rate, and we know the thickness of the chip, and we know the heat transfer coefficient and the ambient temperature, that means that we now know the surface temperature of the chip. So we do have enough information now to define the second boundary condition, which is that the temperature is equal to these terms at Y equals L. So the first boundary condition, again, is that the base of the chip is insulated, and the second boundary condition we can only come up with by way of the energy balance. So I've equated two different ways to define the flux at the top of the chip. So let's use that second boundary condition to solve for the second constant of integration. So we know that the temperature is equal to the temperature of the surface of the chip at Y equals L. So that's equal to negative Q dot over 2K L squared plus C2. And the temperature of the surface of the chip we defined by way of the energy balance, which was Q dot L over H plus T infinity. Solving for C2 now, we find that it's equal to Q dot L over H plus Q dot over 2K L squared plus T infinity. So making this substitution for T2 will give us a final function for the temperature profile. After making that substitution, we come up with a final equation for the temperature profile. A couple of things worth noting is, let's think about this profile real quick. If the chip wasn't generating any thermal energy, let's say you turned it off and you let it come to steady state, that means that the temperature of the chip is uniformly equal to the temperature of the room throughout it, which makes sense. You turn the chip off, eventually it cools to room temperature. If we think about perhaps increasing the heat transfer coefficient, we could do that. We could increase H by perhaps blowing air more rapidly over the chip, or maybe we use water instead of using air. What we find is that the temperature of the chip will decrease because we're cooling it off more rapidly. Something similar would occur for T infinity. Of course, if you had a colder room, the temperature of the chip would also be colder. And if we increase the thickness of the chip L, it's not surprising that the temperature of the chip itself will increase.